All right, this note section is going to be over ionization energy. So first you have to know what ionization energy is. So ionization energy, which I'm going to shortcut today as IE, is the energy required for the complete removal of an electron from an atom or an ion. And so to dumb this down, we're asking how much energy, how hard do I have to pull to try to take an electron away from an atom. So this is how hard is it to take away an electron from an atom. So if it is very difficult to take an electron away, that energy is going to be big. And if it's very easy to take it away, that energy is going to be small. And so to be able to take an electron away from an atom, you have to overcome the attraction between that electron and the nucleus, which is positive. So we call that a Coulombic attraction, the positive and negative. Okay? So we're going to study later in the lesson that atoms with more than one electron can lose more than one electron. Someone can come in and keep taking multiple electrons. And so there are multiple ionization energies. We're going to start talking just about what's called the first ionization energy, which is coming in and trying to remove the first electron that you can, which is pretty much always the electron that's sitting furthest away from the nucleus. So the outermost electron. Okay, but we do use a little subscript 1 for that first electron we take off. And then if we take off a second electron, we put a little 2, and on and on and on. Okay, so we're going to look at some atoms to come up with a general trend, and then we're going to look at, there are lots of anomalies with ionization energy, and we don't get to argue this. We just have to see what happens in nature, who's hardest to take away from, who's easiest, and we have to go with that and try to explain it. So we're going to look at first 3 atoms on the periodic table that are in the same family. So lithium, sodium, and potassium. These 3. So we're going to look at seeing if we can figure out how hard it's going to be in comparison to take an electron away from each one. So for lithium, if you're going to come in and try to steal an electron, the one that is going to be the easiest for you to steal is the one that is furthest away from the nucleus, and the highest energy level. Okay? So we're going to take that electron out there, that valence electron. Same situation for sodium. We're going to take this valence electron. And finally for potassium, we're going to take this valence electron. So if we wanted to rank and to compare what happens to the ionization energy, who's the hardest to take away from, who's going to be easiest to take away from, the potassium electron is the easiest, and the lithium electron is the hardest. And that is simply because of the distance between that electron and the nucleus. The nucleus is the thing fighting you to try to hold on to that electron, and you're trying to take it away. So the farther away that electron is from the nucleus, the easier it is going to be to take away. Okay? So what we're going to learn is a general trend, and there's lots of issues with ionization energy, but a general trend. These 3 elements are in the same family, but we stacked them on top of each other in the periodic table. They are in the same group there. Ionization energy is going to decrease as you go down the periodic table. Because you get more energy levels, each sequential period has more energy levels, which means their valence electrons are farther away. So ionization energy decreases down the periodic table. The one that's harder to figure out is, again, if they're in the same period on the periodic table, it means they all have the same number of energy levels. So if we examine lithium, beryllium, and boron as you go across the periodic table, okay, in general, if you're looking at the electrons, if you're going to take the electron away from beryllium, it's going to be one of these 2 that are sitting at energy level number 2. Doesn't matter which one. They're both going to be equivalent level of energy to take away. Okay, and then boron, same thing. We're going to take away one of those electrons that's sitting up there. So these electrons all appear to be roughly the same distance away from the nucleus because they're all sitting in the second energy level. Okay? However, if we had to compare them, the hardest to take away from in this setup, okay, in general, ionization energy is going to increase across the periodic table. Because as you go across the periodic table, even though the distance is staying relatively the same, there are more and more protons fighting you. We call that the effective nuclear charge. The effective nuclear charge increases, so it gets harder and harder to take away electrons. However, there are there are two little anomalies that happen as you go across the periodic table that we're going to look at in particular. And so you're not going to have to necessarily memorize these, but what we see in nature, we have to see it like this is what we expect. We expect the ionization energy to increase as you go across, but what we see is little things that don't follow our rules, and we have to figure out why and try to explain that. So atomic radius didn't have very many, if any, exceptions, but ionization energy has plenty. Okay, and so you need to understand what it is that we're trying to do and the structure of the atom to be able to then explain what happens when weird things occur. So there are lots of things that can affect ionization energy. The big ones are the nuclear charge, which is the number of protons, and then the shielding, which is those number of inner layers. But then other things that can happen are the individual sublevels, the differences in the S's and the P's, which ones are harder to take away from. Okay, and then in general the atomic radius. The ones that are smaller are going to be harder to take away from. The ones that are bigger are going to be easier to take away from. Okay, so I have several slides here that are going to go through the changes in ionization energy as we go through the elements in the periodic table. I believe from hydrogen down to neon. Starting with 1 electron down to 10. So if hydrogen is set, this graph over and over and over gives you the first ionization energy, how much energy it would take to take away the outer electron. So if let's say hydrogen's energy was known, how hard it was to take away. If we want to compare helium to hydrogen, okay, if you look at a hydrogen atom and a helium atom, hydrogen atom has 1 proton in the middle, okay, helium atom has 2 protons in the middle, and they both have just 1 level of electrons. Hydrogen has 1 in its first level and helium has 2. So if you're going to come take an electron, hydrogen's would be from its only electron, helium's would be 1 of its 2. So if you're trying to steal one of those electrons away, compared to hydrogen, helium is going to take more energy. Because it has the same number of energy levels, it is roughly the same distance away from that nucleus. Okay, so they both have no shield in there, but helium has more protons. It has a greater nuclear charge. So it is more difficult to take away that electron from helium than it is hydrogen. Okay, so then when we move along to lithium in comparison, so lithium is next up, and lithium has 3 protons and 3 electrons, but its electrons are located in 1s2, 2s1. So when you draw them, we've got 2 electrons sitting in that first energy level and 1 electron in the second. If you're going to take away an electron from lithium, you're going to take one from the outside, from the valence. That electron, even though there's more protons, that electron is farther away from the nucleus than either hydrogen or helium. So when we move on to lithium, what we see is that lithium has a much lower ionization energy than either hydrogen or helium, because it has more shielding. There's that extra layer in between. And that electron is further away from the nucleus, which outweighs the extra positives. That distance is more important. So then we move on to beryllium. I've already drawn the picture of this. Beryllium has 4 protons in that middle, and it has 1s2, 2s2. So when you come take away an electron from beryllium, you're going to take away one of those 2. Well, just like lithium, it's in the second energy level, so it's roughly the same distance away. But now you're fighting more protons. And so beryllium has a slightly higher ionization energy than lithium when you compare them, because beryllium has the same energy level, the same shielding, but it has more protons, has a greater nuclear charge. So it's a little harder to take away. So up next we see the very first one of our anomalies coming up when we look at boron. So if we compare boron to beryllium and lithium, okay, boron has 5 protons, and it has 5 electrons, 2 in that first energy level and 3 in the second. And so when we look at this, we're looking at taking away that valence electron, and we say, okay, well, it looks like it's about the same distance as lithium or beryllium, but we've got more protons in that middle, so it should be harder to take away. And what we see in nature, though, okay, what we see in nature, we go through, we have the same shielding, we have greater nuclear charge, we expect it to be a little higher than beryllium, but what we see in nature is that it's actually a little bit lower. And so we had to come up with an explanation, well, what could be different about beryllium and boron And so when we actually compare those electrons and look at where we've said they are, okay, even though both valence electrons are sitting at energy level number 2, berylliums are coming from the 2s, and borons are going to end up coming from that 2p, that very first one. And so that p orbital being available, p orbitals are slightly higher in energy than the s orbitals, so it ends up being slightly easier to take away from that p orbital. And we had to come up with that because what we expected in nature was it to keep going up, but it didn't. There was a little anomaly. So when we move along to carbon from here, carbon looks the same as its electrons as boron, but it has 2p2. It has an extra electron in there. Well, when we look at this, those two electrons, carbons and borons, they're both from the 2p, so that can't be the difference here. And so when we look at carbon, it comes right back and follows our trend, where we say, okay, more protons available, it's going to be harder to take away from, okay, because they're both sitting in that 2p. So we just see this little weird blip between our s's and our p orbitals when we first start our p orbitals. After carbon, we have nitrogen, and nitrogen follows that same pattern. It's going to be even harder to take away from than carbon because we have more protons. Nitrogen's electrons are all still sitting in that 2p. Okay? And so in general, what we're seeing as we're going across the periodic table, lithium to nitrogen is all in the same period on the periodic table. We're just tracking across so far. And what we see is in general, that ionization energy is increasing. However, we did see a weird little anomaly happen between beryllium and boron. And we're about to see another one happen between nitrogen and oxygen. So this next part was definitely unexpected. When we go to oxygen, we're thinking, well, it should go up because oxygen has one more proton in that same energy level. However, when they actually ripped these electrons away, we found there was another break in the pattern. Okay? And we had to come up with an explanation why. So nitrogen and oxygen both have their electrons in energy level number 2. Okay, here's nitrogen and oxygen. Okay, so their valence electrons are both in energy level number 2, so that can't be the difference. Nitrogen has 7 protons, oxygen has 8 protons. We would think oxygen is going to be harder to take away from. Then we look, and those electrons are both coming from the 2p orbital, so that can't be the difference like it was between beryllium and boron. So then they had to go down even further. Okay, and so the idea here was nitrogen did not have this fourth electron in there. Nitrogen's orbitals look like that. So taking an electron away, we could have taken this one or this one or this one. They were all equivalent. But oxygen has one of these orbitals being filled, and it doesn't matter which one. But now when we look at this and we're going to try to come in and steal an electron, this electron right here is going to be a little bit easier to steal than any one of the individuals. And what the explanation that we've come up with is these two electrons that are sitting in the same orbital. They're both electrons sitting in there, which are both negative. They repel each other. Okay, so that electron sitting in there with it, that little black arrow that's indicated there, helps give a little extra push out when you're trying to come in and take away an electron. It helps kick that electron out just a little bit, making it slightly easier to take so that it's helping you fight against those protons. Okay, so that extra repulsion sitting in that p orbital helps make it a little easier to take from oxygen. Okay, so that's the second anomaly that we're going to see as we go across the periodic table. When we move on to fluorine, we see that it goes right back to our expected, that it's a little bit higher. And when you look at fluorines compared with oxygens, there's no difference between oxygen's extra electron and fluorine's. So then it reverts back to the number of protons. Okay, fluorine has more protons than oxygen. It's going to be harder to take away an electron. And then finally, when we go to neon, we put that last electron in that p orbital. Okay, neon's the highest up there. Okay, and so in general, if you look again, we finished the entire second period. In general, the ionization energy increases as you go across, but we do see anomalies between the S's and the P's, when we end the S's and start the P's, and when we go from P3 to P4, when they were all unpaired, and then when we have our first pair. So then when we look at the next atom, which we're not going to detail all of this, but the next atom would have been sodium. How sodium differs from neon is it has a valence electron at energy level number 3. So that electron, if we moved on to sodium, ends up being much easier to take away because it's now coming from the 3s instead of anything with energy level number 2. So then it tracks through, if you'll look, as we go down the periodic table, from hydrogen to lithium to sodium, ionization energy in general decreases because it's easier and easier to take away that electron. So if you look for hydrogen to lithium to sodium, that is going down because that electron is going further and further from the nucleus. So I have a generic plot that you can look at of all the elements. So going across a period, you will see in general going across a period, we go up. Ionization energy increases. But you'll see those weird blips between S's and P's and P3 and P4. And then when you go down the periodic table, so just to show you 3 that go down the periodic table, hydrogen or helium to neon to argon to krypton. In general, as you go down the periodic table, it decreases because you're getting more and more energy levels. But ionization energy has lots of anomalies. Okay? So what you more likely have to do is they will tell you what it is, and you have to explain why that could be. But in general, ionization energy decreases down a group and increases across a period. Those are in general. Okay, so we're going to try to rank a couple. Okay, so we're ranking them using the periodic table, and I'm going to do just the ones that fit our trends, and then we're going to talk about the weird little exceptions. So we're going to see if we can rank the elements in the sets in order of decreasing first ionization energy. So remember, decreasing means we go from high to low. And so for us, a high ionization energy means it's hard to take. And a low ionization energy means it's easy to take. Okay, so remember, you're fighting against, you're on the outside and you're trying to steal an electron from an atom. You're fighting against the protons. Okay, so the further away that nucleus or that valence electron is from the nucleus, the less battle you have, the easier it's going to be able to take. And then the more protons you have fighting you, the harder it's going to be to take. So we're going to find the 3 elements that are in letter A. We've got krypton, helium, and argon. So krypton, helium, and argon. 3 elements in the noble gas family. So if we look at those, first thing you always want to identify is energy levels, the number of energy levels they have, because that's the most important indicator on all of these periodic trends that we see, these atomic properties. So helium only has 1 energy level, argon has 3, and krypton has 4. Right? And so the hardest one to take away from are going to be the ones that are closest to the nucleus, because that's where the protons are holding them. So helium is going to be the hardest to take away from. The next closest would be an argon, because they're only in energy level number 3. And the easiest to take away are going to be from krypton. Okay, I'm going to skip letter B right now because letter B has one of the little anomalies. So does letter E. So we're going to do the rest of them and come back to those. So then if you find calcium, potassium, and rubidium. Okay, we got those 3 elements right there. So first of all, you got to separate them by energy level. Both potassium and calcium have 4 energy levels. Rubidium has 5. So that means that rubidium is going to be the easiest to take away from because that electron is farther away. So I'm going to put rubidium at the end of my list. Okay, it is definitely the easiest. And then when I have to compare potassium and calcium, the one that's going to be harder to take away from, because I'm taking them both from level 4, is the one that's going to fight me harder, which has more protons. So the hardest to take away from is calcium. Okay, and then we'd have potassium. So then when we go look at iodine, xenon, and cesium, okay, we got those 3 elements. We want to first identify energy levels. So both iodine and xenon have 5. Cesium has 6. So I'm going to right away make my list. I'm going to say, well, cesium is going to be the easiest to take away from. It has those electrons are farther away than the other two. So then I'm going to look at and compare iodine and xenon. And they're both taken away from energy level 5, so the one that's going to be harder to take away from has more protons. So xenon has more protons, it's going to be harder to take away from. Okay, and then the last one before we get to the anomalies, strontium, calcium, and barium. Those are easy, they're all in the same family. Well, these guys have differing energy levels. So if the energy levels are different, that should be the easiest thing to identify first. So the easiest one to take away from is going to be barium, because it has the most energy levels. The hardest one to take away from is going to be calcium. It has the fewest energy levels. And then strontium is going to be in the middle. Okay, so those are the typical ones, and the energy levels are going to dictate everything. The problem comes when the elements are all in the same energy level and we hit a couple of those weird spots. Okay, so the weird spots happened between when the S's ended and the P's began, and when the P's were all unpaired in P3, and when the P's had their first paired electron in P4. So those are the little columns that cause issues. And so that's what we're going to work on in letter B. All right, so if you go find antimony, tellurium, and tin on the periodic table, we can see that they're all in the same period on the periodic table. They all have 5 energy levels. So the difference when we're in the same energy level is we tend to look at the number of protons. And so when we look at this, we would expect that tellurium is going to be the hardest to take away from, and tin is going to be the easiest to take away from because of the number of protons. However, if we remember back to our anomalies, we see that anomalies happen between the P3 and P4 columns on the periodic table. So those families where the half-filled and the one past that occur. And so if I were normally going to rank them hardest to take away from to easiest, I would say tellurium, antimony, and tin. Most protons to least protons. But what we've seen in nature is when these two families are involved, there's a slight flip-flop between them on our normal ordering. So we would put antimony here and tellurium here. Okay. So then if you move to letter E and you find antimony, tin, and iodine, okay, again, they both have 5 periods, five energy levels. And so we look at protons. Here we're not looking at the P3 to P4, that little dip. We're comparing the 50, 51, and the 53. And so that little dip, just to show you, happened only between those P3 and P4 columns. Once we went on to the P5, that went right back to our normal trend. Okay, so when we list on E, we're going to put it like we did before. So hardest to take away from has the most protons. We got iodine, then we got antimony, then we have tin. Okay, so there are some exceptions to that. Most of the time it follows the general trends, but you have to be aware of that. So then up next is when we're going to talk about multiple ionization energies. So we've been talking about just taking the first electron away, but you can take away multiple electrons from an atom as long as it has multiple electrons to give. And only hydrogen has just a single electron. So we just indicate them as different, the first ionization energy, the second ionization energy, and the third ionization energy, and so on and so forth. So the first ionization energy will cause the atom to have a positive 1 charge. Any atom that you take away an electron from is going to end up with a positive 1 charge after you take the first one. When you take the second one, it's going to end up with a positive 2, third one positive 3, positive 4, positive 5, etc., until it's all out of electrons. Okay? What you do have to note is that the more electrons that you take from an atom, the harder and harder that becomes. So just to think about that, when we go back to our little drawings, okay, if you looked at lithium and you took away its first electron, that electron's no longer there. When you go take the second electron from lithium, you're now taking it from an inner energy level. You're taking it from that energy level that's right next to that nucleus. It's going to be harder to take away than that first one. Okay, but that even applies to what if you look at beryllium. If you take away that first electron on the outside, it still has another electron out there. If you try to take away that second electron, it's going to be harder than it was to take away that first one. Because now, even though it still has 2 energy levels, now we have those 4 protons, that are still there, they're only holding on to 3 electrons now. And so they're able to hold them even tighter, and it's going to be harder to rip off that second electron. So as you move along, subsequent ionization energies always get bigger and bigger. Okay, so it's always harder to take the second one than it was the first one. So, and then so on and so forth. Usually what happens is when electrons end up at a filled energy level, usually the atom won't let you take any more. Now we can force it to happen, and we have, but nature doesn't tend to do that. And so what you just saw with aluminum is aluminum has 1s2, 2s2, 2p6, 3s2, 3p1. When you start taking away electrons, aluminum will let you take the first one in nature, will let another atom take it. It'll let you take the second one and the third one. It'll let you take all 3 of those. But once you end up at a new energy level, aluminum stops letting you take them, or stops letting nature take them. So what we see in nature is that aluminum ends at Al3+, and then it stops letting them take away. And so that's what happens naturally. Now we can man-made, we can force them to take more electrons. And that's what we're going to look at next. Okay, so this next part has to do with taking multiple electrons that not necessarily nature would do. Okay, but first we're going to talk about something called the photoelectric effect, which is how we do this, how we take electrons away. And so this is, I believe, Einstein developed this. But how we take electrons away, how do we put in that energy? So it's not like someone with a set of tweezers is going in and removing electrons. What we have to do is we have to hit those electrons, or hit that atom, with energy. And so when atoms are hit with energy and they absorb that energy, those electrons can move to higher and higher energy levels. And the idea is if you put in enough energy and you move them to a high enough energy level, they've basically left the atom. That nucleus has no hold on them anymore. And so we talked about this earlier this unit about electrons moving up energy levels where they could move up and then fall back. But so if you move them up far enough, okay, then they essentially leave the atom. And how we put in that energy is we send in light. And so electrons that are ripped off using this light are called photoelectrons. And so what we do, we learned earlier this unit that light has a specific energy based on its wavelength or frequency. Different colors of light have different energy. And so what they can do is they can hit an atom with some light of a specific color or specific energy, and they can see if an electron popped off. So this is a little short picture of what a process happening with a potassium ion. And so what they did, let's say we hit it with some red light, 700 nanometers, and you could go calculate the energy of that. And the energy is written here in a unit called electron volts, which we don't really use much in this class or at all. We use typically joules. Okay, but they put in that energy, and what they noted is, hey, no electrons came off, which means that I need to put in more energy to be able to pull off an electron. So then let's say they hit it with some green light that had a wavelength of 550 nanometers or 2.25 electron volts. And they noticed that what shot off, that electron came popping off. And what they have is they have a detector on the other side. When they hit it with lights, they have a detector that's going to catch any electrons running into it. And they measure the velocity that electron hit it with. And so we didn't talk about it much, but what they do is they calculate the velocity of the electron when it hits that detector, whatever it is. And we have a formula for kinetic energy of anything that's moving as 1/2 m times v squared. Well, this would be the mass of the electron, which we know. And then they measure the velocity and they calculate the energy that it hit that detector with. And so what they say is, they said, okay, I put in a certain amount of energy, and the electron popped off with a certain amount of energy, and they calculate how much energy it actually required to actually rip the electron away. So I'm going to give you one with simpler numbers here. So if I say I put in 10 joules of energy, and I calculate that the electron popped off, and it popped off with a velocity that gave me 3 joules of energy, I can calculate how much energy it took to rip that electron off as 7 joules. It's simply the difference between what I put in and the energy that I got out. And that's the conservation of energy, that it's not created or destroyed. So the energy I put in, some of it got converted to kinetic energy. Others got converted into that ionization energy that was used to rip it away from from the nucleus. Okay, so that's how we've calculated ionization energies on how much was actually needed. Okay, so to show you further is we knew that green light was enough energy there. Okay, but then what if they hit it with violet light with 400 nanometers? It's even more energy. So what they calculated was that there were 2.0 electron volts needed to actually eject that. And you don't have the numbers here to show that, but 2.25 was plenty. And so then the idea is if they send in 3.1 electron volts, and they know that it needs only 2 to pull that electron off, this electron is going to come flying off with 1.1 electron volts energy. Okay, but they've done that for all of the electrons for an atom. They've ripped them all off, and some of them require more energy than others based on where they are, where they're located, how far from the nucleus, and then how many protons that the atom has. And what they've done with these is they've created photoelectron spectroscopy graphs. And so that's a crazy name for you, but photoelectrons are just the electrons that are popped off. And spectroscopy is us using light to detect certain things. So it's just a laboratory technique to go calculate all these ionization energies. So what I just described is the actual device that they use. So that light coming in to the sample and then the detector to get those electrons, and then they calculate the energy that was needed to actually rip it off. So you don't have to worry about calculating it, but what happens is they make these little graphs. Okay? And this is actually, we're kind of doing this backwards. These graphs are where we came up with the electron configurations. Okay, it wasn't that they just decided the P's and the S's and all that kind of randomly. This is where we got this data that there are different shaped orbitals in the same energy level and whatnot. Okay, so these are PES graphs where what they are is they're marking how many electrons took a certain amount of energy to rip off. And so there are 2 kinds of these graphs that I'm going to show you, 2 different ways this could be pictured, so I'm going to explain them both. But what's on the x-axis is the energy that it took to rip off the electron. And then what's on the y-axis is how many electrons got ripped off at that energy. So this is where we locate, okay, how many were in that orbital? How many were in this orbital? Okay? The weird thing about this version of the graph is it has 2 x-axes. Okay? The reason it has 2 x-axes is that if you look at the actual scale of the x-axis starts at 0 and ends at 100. To go from 0 to 100, if I made you make an x-axis, you would probably want to count by tens, not by ones. But if you're counting by tens, each block on your graph counting by tens, it's going to be very difficult to see the difference between 1.4 and 2.4. And so what they did is they said, okay, I have 2 little blips on my radar or my detector that happen between 0 and 10. So I'm going to make one of my axes between 0 and 10, and I'm going to count by ones, so I can see the difference between the 1 and the 2. And then I don't have another blip until 40, 39.6, so I'm going to go count by tens to 100. Okay, really this whole axis would be placed at the end of this, so it would go really long over here. Okay, but they just stack them on top of each other to make it easier. And so what you do when you read these graphs, now that we know the electron configurations, is you have to figure out which electrons would be the easiest to remove and which electrons are the hardest. So remember, this is all one atom, one single atom with all its electrons. So if you look at this, first of all, this one said we had 2 electrons that were at this level, 2 electrons that were at the 2.4, and 3 electrons that were at the 1.4. Well, that's a total of 7 electrons. And so what I can do is I know the atom that has 7 electrons is nitrogen. So this is nitrogen. The other thing that I can tell is now I can understand where the electron configuration for nitrogen comes from. Nitrogen's electrons we have already talked about this year are 1s2, 2s2, 2p3. Now, I already gave you that answer, but this is where they came from. And so what they said is, well, the easiest electrons are going to be from the ones that are furthest away from the nucleus. And so these electrons right here are the furthest away from the nucleus. Okay? The ones that are hardest to take away are always from the ones that are closest to the nucleus. And so the highest energy was the hardest to take away, which ones would be the closest energy level. So those are my 1s2 electrons. These are my 2p3. Okay, these guys are my 2s2. And so where they noted, if you look at the 2s2 and the 2p3, those are really close in energy. And so that's where we got the different orbitals, but the same energy level. Those are very close, but there's some difference between them. Versus the different energy level, the energy level 1, those are drastically different. 1 and 2 versus 40, that's a big gap. And so that's where we're looking at the difference in energy levels and the difference in orbital shape. Okay? So this next drawing, you can tell that next element has a total of 8 electrons. So I know this is oxygen. Okay? And I've learned already this year that oxygen is 1s2, 2s2, 2p4. Those are my 8 electrons. But now you can see them on here. The hardest electrons to take away are from the 1s2. Always. Those are always the hardest ones to take away from any element happen at energy level number 1. Okay? And then, so the next hardest would be from the 2s2, and the next hardest would be from the 2p4. So that's where we got those. So when you look at these graphs, you want to work from the highest energy to the lowest energy when we actually write their electron configurations. Okay? So the other thing that I wanted you to note on these in comparison, there's two things. Okay? If you look at the two atoms, we got nitrogen and we've got oxygen. They both have electrons in the 1s2. Okay? And they're both the highest energy level. However, oxygen's 1s2 were so much harder to take than nitrogen's 1s2. And if you look at it, try to explain why, okay, I'm only going to draw where the 1s2 would be. Those first 2 electrons in energy level number 1. When you're getting down to try to take those electrons away, for oxygen you're fighting against 8 protons, and nitrogen you're only fighting against 7. That's why it's harder to take them away from oxygen. The other thing that I wanted you to note is this is where we came up with our little anomalies. Okay, on the ionization energy, is that when we look at the easiest ones to take away, okay, we would think that oxygen having more protons would be harder to take away than nitrogen. But when we look at that, we see that little decrease that oxygen is actually easier. And it was harder on the 1s, but it was easier on the outside, and that's where we came up with the 2p3 and the 2p4, the little blip. Okay, so we're going to look at a couple more, and I'm going to show you where the d orbital idea came from. So if you look at the graph on the left, it has 3 x-axes. We've got a 0 to 10, counting by 1s. We've got a 10 to 100, counting by 10s probably. And then we've got 100 to 500, probably counting by hundreds. Okay? And so they use 3 x-axes because we have all these little blips on our detector because there's tons of electrons in this one. So if you add up all the electrons, I believe you have 20 electrons, which you could go find the element. But we're going to work our way through this with electron configuration only. So what I want you to look at is you want to identify where the hardest electrons to take away were. Those are always the ones that are closest to the nucleus. So those electrons right there are the hardest to take away from. Those have got to be your 1s2. Then you just want to go in order. The next hardest to take away, those are your 2s2. Next were your 2p6. Next hardest to take away would have been the 3s2, then the 3p6, and then we've got our 4s2. And that leads me to what calcium is, which is those 20 electrons. So if you do note, though, the electrons that are in the same energy level are relatively close in energy, where the ones that are in different energy levels, like the 1s and the 2s, and the 2 are the ones in the 2s and the 2s and the 3s, those are where the big gaps happen in the energy. Okay, energy levels are much more important than the individual orbitals. Okay, so there's our calcium. If you look at the very next one, the one to the right, you see that there's an extra little blip right here compared to that one we just did before. There are 21 electrons here. Okay, and if I look at the 1s2, the highest energy, I see that it's harder to take away from than the 20 because I have more protons there. So it must be an element that has more protons. Okay, but if I'm tracking through, then I go 2s2, then I get 2p6, then I get 3s2, and then I get 3p6, and then weird stuff happens. And so if you're looking at the atom that has 21 electrons, you're going to identify scandium. When we do these electrons, I talked about this a little bit the other day, when you take off the electrons, you're going to start from the outside. Okay, so the easiest to take away from are these ones that have the little peak of 2. That's going to be my 4s2. So the question is, what the heck is this little peak right there? And so that's where they got the idea that the 3 Ds must happen after those 4s, must be filled after those, but they are tucked in on the inside. They are in energy level number 3, so there's our 3D1. So that's where that came from. It wasn't random that the Ds are always one behind. It's that when they started taking them away, they noticed that they were harder to take away. They must have been on an inside level. Okay. So the other way that you can see these PES graphs are a little bit harder to figure out what element it is, but they show the energy levels a lot better. You can see the groupings. So this one is a little different because there is no scale on the y-axis. It just says relative number of electrons, and you have to figure out what the y-axis is counting by. So it doesn't always count by ones at each line, so you got to be aware of that. So you have to know a little bit about the atom. Okay, but what I do want you to see is the big gaps between the groups of peaks. So these two peaks that I just highlighted in pink, they're very close to each other, which that tells us that those electrons must have been roughly the same distance away from the nucleus, but those are our different orbitals. Where these two peaks over here that I just highlighted in blue, those are pretty close to each other, and there's a big gap between these. So the big gaps that you see are the energy level differences, and then the smaller gaps that you see are the orbital differences. Those are the S's and the P's and the D's. Okay, so what you want to do for these graphs is you want to go figure out where the highest energy is, which is the hardest electrons to take away. So you go look at this and you go, okay, this is my highest energy. Those are the hardest to take away. I know that those always happen in level 1, and I know that level 1 has only the S, and I can fit 2 electrons in there. So then this line must be the 2 marker, which then means on this graph, okay, then I am counting by ones, because that's 1, 2, 3, 4, 5, 6. So that makes it okay, fairly easy to do then. So then we go find the next highest, which would be the 2s, and that would be up to the 2, and then we hit the 2p, and that would be up to the 6, and then we hit 3s, and that would be up to the 2, and then we hit 3p, which is the 4. And so that element is sulfur. Okay, so we're going to try another one, and then I have a modification to make to it. So again, you look at this and go, okay, where's the highest energy? Right here, there's our peak. So that must be energy level number 1, S, and that must be the 2 marker. So again, this is the same as before, but I'm going to show you a modification where it's a little different. Okay, so then we have our 2s2 and our 2p6 and then our 3s2. So then this is going to be magnesium. So I did want to alter this a little bit to see if we can follow this. So what if, ignoring the ones that are on the picture, this is the graph that you were given. So imagine just the peaks that I've scribbled in black, ignoring the other ones that were there originally. So you would still go find the highest energy, and you would say, okay, that's energy level number 1. I know I only have S. This must be the 2 marker. I sure can't fit 4 in the 1s. So this is my 2, so that's my 1s2, and I've got to figure out what I'm counting by. Well, if that's 2, then halfway to that 2 has to be 1, so this up here is 3. And so when I go find the next peak in the black marker, then this is 2s, and it's just 1. So that element would have been lithium. Okay, so if they don't mark it, you got to be really careful on those. Okay, so that's ionization energy, and we've got one more trend to do at a later lecture.